Anyway, this is something that I have been thinking of for a long time. And it comes from my work on turbulent fluid flow, which is an example of the second law. But it has led me to a wider perspective on the second law. But if we just start with this mysterious second law, and which seems that nobody really understands what it is, and it is surrounded by lots of mystery. So we can start with some questions here that I put up on my blog for today's talk, to start with the questions. And then there is on my blog, there is a lot of material for anyone who is interested in following up on details. But let's start with the questions. The basic question is why certain systems in reality are irreversible when the basic laws of physics are reversible. How can it be? And this is sort of the mysterious question that if you go to quantum mechanics or some form of mechanics, the laws appear to be reversible. But in reality, physics is not reversible. And that connects to the arrow of time, why time is going forward, why it is impossible to retrace backward. If you have gone into the woods, then you cannot find your way back. And then you have the mystical concept of entropy. And as von Neumann cleverly said, that if you want to win a discussion, you can just draw in the concept of entropy, and everybody will be confused because there is, okay, so now something happened on the screen. But okay, so he said that bring in entropy, and that's a good subject because nobody knows what it is. So the question is, what is entropy? And then you have Boltzmann statistics that says that S, the entropy, is somehow related to the number of microstates, which is also mystical. And in my opinion, statistics is not physics. Statistics is something that an insurance company can do, but physics cannot do statistics. That is, accumulate lots of data and take mean values. Well, there is something called the classical second law in thermodynamics, where you have temperature and you have the change of entropy, ds, equal to something called Q, which is some kind of heat, and that is supposed to be bigger than zero. In particular, then, since temperature is positive, it says that ds has to be bigger or equal to zero. And the question is, why is it so about this mystical quantity of entropy? Okay, so if you just scroll up a little bit there, then my experience from turbulent flow says that, well, you don't need the concept of entropy because there is another concept that is physical. And the trouble with entropy is that it has no physical meaning, and then you can worry about it. What can it be? But there is something related to entropy that is turbulent dissipation, which is physical. And turbulent dissipation has a sign because it is a loss. And therefore, this Q appearing on the in the TDS formula, that you could as well think of that as turbulent dissipation, and that gives you a loss, and this loss cannot be retrieved. So then you have to go into the nature of turbulent dissipation. Why is it, does it come with a sign? And this is because turbulent dissipation is the formation of small-scale kinetic movement, small-scale vortices in the flow, coming from input of large-scale kinetic energy. And the small-scale kinetic energy appears as heat, but it has a small scale. And it is a necessary ingredient in fluid flow, because in a flow, you have a reorganization of the flow, creating strong gradients. And these gradients cause this dissipation into a cascade of small vortices, which appears as heat. And it is irreversible, because the small-scale kinetic energy, which is not organized, cannot be organized to large-scale kinetic energy from where it comes, because of finite precision, and this appears in computation. So in my view, you can resolve the mystery of entropy by replacing statistics by finite precision computation, which means that you cannot retrieve from something that you have been split into little pieces. When you smash the egg, drop the egg on the floor into little organized pieces, there is no possibility to reshape the egg, because the precision required is not available in computation. And then, in my view, you can view physics as some form of realization of computation. And on the larger scale, you can see the necessary appearance of turbulent dissipation is because you have in nature, in many forms, a competition with forces that increase difference, that that form sharp gradients. And if there is no stop to the increase of difference, then you will have, the system will break down. So at some level of sharp gradient, of very sharp differences nearby, a mechanism must set in to decrease difference. And that is the turbulent diffusion. Without that, the system would explode and the physics would finish, but it does not finish. So that is, in short, an explanation of the necessary appearance of something of the form turbulent dissipation, which is impossible to reverse because of finite precision. And then you can formulate then, if you scroll up a little bit, the conventional laws of thermodynamics. So you have one concerning the energy, that the change in energy plus work is equal to Q. And the Q there is the turbulent dissipation. And correspondingly, you have for the kinetic energy minus work is a loss, which is minus the turbulent dissipation. So in this form, you have kinetic energy, you have heat energy E, you have kinetic energy K, you have work W, and you have Q, which is turbulent dissipation as a loss, which comes with a sign. And this is the second law without entropy, where Q has a clear physical meaning as turbulent dissipation. And you can compare it to the classical, where the Q instead is thought to be temperature times the change of entropy, which is then gives, if Q is positive, necessarily ds is also positive, but you don't need the entropy. It is sufficient with Q, the sign of Q. So as a summary, I can the summary is that physics is viewed as a form of finite precision computation. But the physics also has instabilities, which is building up of sharp gradients. And to combine these two, there must be a mechanism to decrease sharp gradients, to split it into little pieces in the form of heat. And as an example, you can take the famous Joule experiment, where you have, which Joule did. So we had a bucket of water, and in the water he put in a combination of two chambers connected by a channel. And in one chamber he had a hot gas, and in the other nothing, let's say. And then he opened the valve and recorded. Okay, so the gas inside the hot chamber at high pressure expanded into the empty chamber, and that caused a cooling. And then he was expecting to see a decrease of temperature in sort of this setup in the bucket of water, but no change of temperature was recorded, no loss of energy, and he was very confused about what happened. In my setting, and you can do the simulations, you see the gas from the hot, dense chamber go through the narrow channel into the empty chamber, and it decreases in temperature because it expands. And this you can also see in these formulas, where the sign of the work has a sign in expansion and another in compression. So it means when the gas is expanding, W is positive, and it means that the kinetic energy increases according to the formula. So the gas speeds up and enters the empty chamber, and there eventually it is turned into turbulent. Through turbulent dissipation, it is turned back into heat, and the gas comes to rest in both chambers. And there is also a gap between. It is not the equilibrium state finally reached. Depends on sort of the dynamics of the system, the width of the channel, and so on. But this Joule experiment carries a lot of information about the second law of which is in the formulas with the W, the work of different sign, and Q, the turbulent dissipation of positive sign. And all of this you can find in detail in computational solutions of the Euler equations for a compressible fluid. And then if you look at the Euler equations just without any form of viscosity, they seem to be reversible. But if you solve these equations with a good computational method, you will discover flow, and you will discover that the flow becomes turbulent, and that there is a turbulent dissipation necessary to keep the system going. So you find that in a book on the left side here on my blog. You find lots of material, and you find also in the book Computational Thermodynamics. And the related problem is black body radiation, which concerns also an irreversible phenomenon of radiative heat transfer that goes from warm to cold, but not the other way around. And there is a lot of mystery also in climate science about back radiation as some kind of flow from cold to warm, which should cause some global warming. And there is also, if you list on the presentations I have given, there is one I think is worth listening to. On the presentations there, you find misunderstanding Planck's law, which gives also insight into the irreversible nature of radiative heat transfer, which has a different origin than turbulent dissipation. In the case of radiative heat transfer, the irreversibility comes from a high frequency cutoff, which is also related to finite precision. It means that the hotter object can carry higher frequencies and so is stronger than the colder body, and therefore through these high frequencies can transfer heat to the cold, but not the other way around. So this is there is lots of material on this that I can show in detail if I had the screen, if I could share the screen, but I don't know why. But maybe I can open to discussion. I think I have presented the basic material, the questions, and a resolution based on finite precision plus instability as explanation.
Well, thank you very much indeed. I try to bring everything back, so
yeah.
So you're not seeing my screen. And but by the way, in the short time available, we might have another try at your sharing the screen, because there's a lot of information there. I'd like to thank you very much for having supplied all that information to me, because when you said you wouldn't be able to give the lecture today, I was concerned, but I tried to persuade you maybe to give me some material, and you did more than that. You gave me this material, which you've just gone through. You gave me a link to a video, and you gave me a number of other very interesting pages from your blog, which was fine. I just would have felt that I was stumbling a bit trying to give it myself. But there's a lot of information there, and
but maybe you could just put it up for anyone who is interested.
Yeah, there's so much there.
Not now, but in some kind of footnote or something to the talk.
Yeah. Okay. And in particular,
maybe. But anyway, I think what would be interesting is to have some kind of discussion and see if anything of what I have said is understandable and makes sense. And then for anyone interested, there is lots of material and details to go into. But I think maybe we could have this discussion now.
Yeah. Okay. What I'm doing, actually, just pardon me for a second, I'm just looking at the comments, because having that as my full screen, I wasn't able to look at the comments.
Yeah.
There are a couple in the private chat which we'll deal with in a moment. Let's just see the comments. Are there any specific questions that you want to address to Claes before we start a more detailed discussion? I'll just go through them quickly here. These are just mainly conversations between people participating through the social media. Quest said he's unfamiliar with some of these technical terms. Well, unless you've studied thermodynamics in detail, some of the terms might confuse you. Okay, let me see. Yeah, I'm not quite sure what shockwave is getting at there, but presumably he's referring to the dual porous plug experiment. He says the experiment he's talking about had a valve, so it's a closed system, I think.
Yes. It is a closed system. Yes.
Okay. Because the classical thermodynamics basically refers to closed systems, as far as I understand it. And incidentally, we've had some discussions in previous weeks about, say, the universe being finite as distinct from being infinite. And if it's finite, there are some of these thermodynamic problems which arise. For example, how come that we get more order as time goes on, according to conventional cosmology? But if it's infinite, perhaps those quandaries
No, but
disappear.
it is, you could think of it as this increasing difference and decreasing difference competition. It is the anabolism and the metabolism of your body. In the anabolism, okay, so you build, and the metabolism you break down. So this to build, to break down, that is sort of the whole process going on. And building structure, that is not against the second law. It is possible to build, and it is all the time building is going on, with and break down. So it is so much confusion with the standard idea of entropy and the disorder and so on. It is just confusing. It is not physics, so this is what I try to help out with. Forget about disorder. Forget about that heat death and so on. It is. You can build your body. You go to the gym, can get bigger muscles. So it is possible to build. Okay, then eventually you will break down. But this is.
So your concept, in particular, in dealing with this important subject, have actually attracted a lot of attention. Maybe it's a bit of a welcome distraction from what we've been talking about in previous weeks about things like relativity and so on. But we've got quite a number of people participating in the green room, and
Yes.
I have a number of requests for conversation. So I'm delighted to be able to accept those before you disappear. So would anybody in the green room like to wave his hand? There's John Hodges is waving his hand, so I'll bring you up first. And Nick has just come in second there. So, John, what are your comments or questions?
Well, thanks, Klaes, for the presentation. I found it very interesting, food for thought. My background is I've been trying to model entropy in my system, and I've built up a stack that must be close to 0.5 meter high of papers, and haven't gotten anywhere.
I just said.
So now let me try to rephrase what I think you're saying to me. You're talking about computation. You mean by a computer?
No, it is no. It is more wide. You think of a physical system sort of at one point in a state, and then it is, in some sense, it will evolve into a next state by some kind of interaction of forces. And of course, you can mimic it on the computer, but it is more like viewing a process as a form of, as the result of a successive number of steps of some, go from one thing to the next and share information. So it is a wider concept. It's not on a computer. I think of physics as a computational process from one line to the next.
Well, the computer does a couple things, and perhaps I'm leading. One, it has determinism. So you're accepting determinism, I think, in what you're saying.
Yes, but it is also with finite precision, you don't have complete determinism, because there is also, if you chop the digits, depending on how you chop the digits in your computation, you get different results. But this is also an interesting question. How the level of precision, if you use single or double precision in a computation, how much does that affect the final result? So there is some finite precision, but physics also has some finite precision. And what is interesting is that the macrophysics is not dependent on exactly the level of the finite precision. So you would have the same universe, so to speak, if you computed it in single precision as in double precision. So that is something that the macrophysics is in a way independent of the actual level of the finite precision, which makes it in a way then universal. Because if it depended on the level of finite precision, then macrophysics would be completely unpredictable. But macrophysics is predictable because it does not depend on sort of the limit of finite precision macroscopically. So that is an important.
That's why you don't use a statistical approach.
No, I say statistics is not physics, because physics is not an insurance company. So statistics is, just an illusion, and it is a confusion. Forget statistics, because it cannot tell you anything of value in physics.
Does that also apply to quantum mechanics?
No, yes, of course, yes. I worried about, yes, of course, everything about statistics in quantum mechanics is nonsense. It is not so that the electron, it is not so that the hydrogen atom, okay, this is the most predictable and stable system in the world. It does not run by, throwing dice. This is completely ridiculous. So it's the same thing.
Anything else before we move on, because we have a number of other requests?
Causation. Causation. Is causation in your mind?
Yes, causation. Yes, there is causation, because, as I said, macroscopic physics, there you have causation. But in the microscopics, it is like if you view the flow of air around a wing, it is the turbulent flow. The minuscule details of that flow is unpredictable, but the macroscopic lift and drag of the wing is completely predictable. So macroscopic predictability is a fact, causation macroscopically, but microscopically it is not fully predictable, because there is, depending on the little details, you cannot know that exactly. But macroscopically, it doesn't matter.
I see, Claes, that one of your quotations on your blog is from Leucippus, who was the teacher of Democritus. This is, nothing is created by coincidence. Rather, there is reason and necessity for everything. So that might be the...
Yeah, there is reason for everything macroscopic. There is reason, but that is what counts. The microscopic details. It doesn't matter, and it's impossible to have full insight. But it doesn't matter, and the level of precision is then sort of in a way irrelevant. The size of the atom of a hydrogen atom doesn't matter. It could be twice as big. The universe would look the same.
Well, Ian.
All right, so John. We have to move on. Did you have more questions? Would you mind if we maybe stopped it and we could bring you back if necessary? Or one quick question. No, thank you. Sorry for cutting you off a bit, but I think there are people getting a bit impatient. They want to come in, and I want to give everybody.
Please.
So thanks very much for your contribution. If you want to come back and there's some time at the end, please wave your hand again. Thank you, John. Now, the next person, I think, was Nick, and after that, Slobodon, because I'm trying to see all your hands. So, Nick, you're up now. What's your point or points? Can't hear you. No, you're mute. You'll have to unmute yourself.
Yes. I'm mostly here to say some introductory words to Kent Mayhew, who I think is the #1 expert on thermodynamics today. And I definitely want to thank Claes for his original critical thinking. And I believe that Kent and I shared going down that same path of critical thinking about the problems with conventional thermodynamics. And before I yield to Kent, I'll make a few general comments that I think echo what John Hodge was talking about. Originally, the current thermodynamics was developed to explain what's happening in steam engines. So it was focused totally on a closed system, which was a fundamental problem with the original and existing thermodynamics. And the second problem was that it was statistical, which I agree 100%. In fact, as a problem of not being pure physics. And when I saw how successful Kent was in taking a different approach, it also automatically appealed to me. Why someone should take exactly that same path in redoing quantum mechanics from a statistical system to a physics system. But Kent has taken a different path of resolution, so it might be quite interesting to Claes to compare his thinking with Kent's thinking. So maybe out of order, but I will yield to the next speaker and recommend that Kent be brought in at some quick point.
Well, thank you very much for that, Nick. We'll do that. We'll bring Slobodan in next, and then we'll bring Kent in.
Yeah, thank you.
Else. So thank you very much for that introduction. So you asked for the floor, didn't you, Slobodan?
Sorry?
You asked to speak, did you?
Yes, I did.
You're very low. We can hardly hear you.
Okay, I come closer to the mic.
That's a bit better. Yeah.
I don't have means to amplify or whatever. Right?
Okay.
I appreciate your.
And if you could speak a bit louder, please.
Yeah. Essentially, you accept the second principle of thermodynamics on one side, and the concept of entropy.
No, I don't accept that.
Okay, but you are relating the entropy to the dissipation, turbulent dissipation, right?
Yes. Yes.
So you're kind of explaining the kind of not that clear concept of entropy by dissipation.
Right. Exactly.
But it would be interesting to relate it more to the historical aspects. As
no, but
I would say that experiment of Joule, right?
Joule
comes close to what Carnot had it in his work. He had it that heat is total differential.
Yes, it is. I mean, it is true that if you go to compressible flow or Euler equation, say if you take a perfect gas, you can introduce a quantity depending on temperature and pressure, which you can call entropy S. It is a quantity defined in the other. So but it has no physical meaning. So this is a very special case for a perfect fluid and so on. So it is possible to have a quantity named S, but again, you have to explain why it cannot decrease. So and this concept has no real. It's not clear what it means. You say it's something with the volume, okay, so bigger volume, bigger entropy, and so on. But it has no direct physical meaning. Whereas my idea is to have just the physical quantities,
Yes. I will come to that, but first, that you mentioned that how definition of entropy, it was Clausius, right? And he did it after Claperion's, kind of popularization of the Carnot's work. And Claperion had it that integration divisor, like T, temperature. as dependent on the nature of the working body. And in spite of that, Clausius introduced the entropy as a quantity which total differential exists.
Yes,
And
fine.
So it's
but
like
the
an
question
integrating factor. You
Yeah,
take
but the
an
question-
imperfect differential and bring in an integrating factor, you get a perfect differential.
So, if you explain the entropy by dissipation, then that should mean actually that you accept at least some of the formulations of the second law of thermodynamics.
Well, but it is. I state a second law without the concept of entropy, but of course, in special cases that we have talked about, it is the same because you can phrase it in different variables, but it remains to explain why this quantity cannot decrease. If you introduce it, why does it have a sign?
How
This
about
must be explained.
Can it be decreased? Can the entropy be decreased in process of, for example, formation of vortex? Actually, there is one guy, Wilhelm Bauer, who formulated the reduction, actually annihilation of entropy in the process of the vortex formation. That's in direct contradiction to the second law.
No, but first of all, if you say that it can decrease, you have to explain.
This is kind of reverse process of what you have been talking about. You are talking about the entropy as a dissipation, but actually
Yes.
out of heat and pressure, spontaneously or by induction, the vortex get formed. So unordered flow of some molecules enters into ordered flow to form a vortex, like toroidal vortex.
Yes, you are right. Yes, you are right that heat can produce organized kinetic motion. Of course, if you have this joule,
it does that.
Yes.
It does that at the expense of the reduction of unorderedness.
No, it is not that. Anything that is expanding, okay, from if you have something hot, if you let it expand, it gives rise to kinetic motion, which could be organized, but you cannot reverse that process. So it is possible from heat, because it's the heat engine and the steam engine. From heat you can produce kinetic work, but it is a limitation in this process of conversion of heat to kinetic work.
But that's introduced later. But Carnot itself, for Carnot, the same amount of heat that the working body takes for the hotter reservoir is returned back to the colder reservoir.
Yes, it is possible. You can have you can have exchange between heat and kinetic energy. Sure, but there is a limitation of that, and that is the irreversibility.
So,
okay.
According to you, is the perpetual mobility of the second order or first order possible?
Well, I mean, it is if you say that if you state a law of thermodynamics that includes entropy, I say I don't know, I don't understand what you're talking about. So if to accept that, I don't know what should I accept because I don't understand it.
Yeah, there is.
Yes, you don't use that definition.
No, because I don't understand it.
Just briefly. Very kind of the so-called unusual.
So Slobodan,
that actually has those features. Okay.
Yeah. I'm sorry, but I think we'll have to move on. Thank you very much for raising this point and making it quite clear about Claes's position, because some people might have been confused. So thank you very much for that contribution. And let me just see where we are now, because it's funny. I'm just trying to bring Slobodan down, and I don't see him here. Oh, here he is. Yeah.
Okay.
Just taking the camera out. So now, so anybody else? So it appears that Kent may want to say something. Okay, he does. So I'm going to bring you up, Kent. And I know Nick has referred to a video of yours.
Well, first of all,
make
a great introduction. I don't know, anyone hear me?
Yeah, you're echoing a bit, but we can hear you. Just make sure you continue to speak up.
First of all, I went through your paper 2008, with Hoffman and Nazarov, and I've gone through it pretty thoroughly. I've written about 20-page response to it. I sent you the first part of my response.
Yes. Thank you. Yes.
If anybody wants a copy of that response, I don't know what you may want to tell me where I can put it. It's in 4 or 5 papers right now, about 20 pages long. Okay. The biggest issue with thermodynamics is we don't respect the fact that the atmosphere has mass and is in a gravitational field. Okay. So when a system expands, it's got to lift the overlying mass. So the part of the atmosphere that's overlying. Okay. The overlying mass is what creates pressure. So it's got to be able to lift that overlying mass. Nowhere in thermodynamics do we deal with that. Okay. Now you've got to understand that once when we lift the mass, if I lift a weight, a barbell in my hand, I've transferred energy from my body to the barbell. If I let go of that barbell, it never comes back into my arms or my body. It's lost. So that's lost work to me. Same thing happens when a system expands on the Earth's surface. It expands, it lifts the atmosphere, okay? And all of a sudden, the atmosphere has an increased potential energy. When that system collapses, the expanded system collapses, that energy doesn't return to that system. It has lost work to that system. Therefore, what happens is the potential energy in the atmosphere, the molecules start dropping down, the ones that are over the system that's collapsed. And when they drop down, they change potential energy into kinetic energy, and that's like a temperature increase of the atmosphere. So at no point does an expanding system here on Earth's surface ever get the energy back that it uses to lift the atmosphere. You've got to realize
I agree.
We go to your Joule's experiment that you were talking about vigorously, right? Think about it. There's no lifting of the atmosphere in that experiment. Okay? So when you open that valve, it just expands into an evacuated second vessel. Vessel 1 into vessel 2.
Yeah.
There is no lift. There's no work done. That's why you don't see a temperature change. Okay? But mind you, people have done that experiment in the 20th century with more exacting things, and they've seen a very moderate increase of the temperature in vessel 2 and a slight decrease in vessel 1. Now I know that you tried to explain that by diffusion and shock and second wave shock and all that. I disagree with that. I agree with Hugo Hernandez, who wrote a paper once on the Guy-Lussac paper. Okay, and what happens is if you take a look at if you take a look at a spectrum of gas molecules, some molecules have a little more energy, some have a little less. The first molecules to get through the valves are the ones with the more energy. Therefore, you get a very subtle temperature increase in the second vessel, and you get a very minor temperature decrease of the first vessel. Okay. The whole energy remains the same.
Right. This is a very important concept. But Kent, could we hear Claes's response as to whether he thinks that
I thought we had 5 minutes here, so
parameters that you talked about are essential to considering the thermodynamic equilibrium, or whether they're sort of another factor. What's your position on this, Claes?
Sorry about that.
Well, I think I think we agree.
I think we understand the main point that
we agree on the presence of losses that are sort of irretrievable. So, and I call that turbulent dissipation. It is irretrievable for some reason, and I try to give a reason why it is not the system is not reversible. So once you have, created this, also in the Joule experiment, once you have created turbulent dissipation, you cannot get it back to the original state. You cannot get the gas to go back to the other chamber. And also you can expand the Euler equations and adding gravitation to it, and you have the same thing. It is also in the atmosphere you have turbulent dissipation as an effect that effectively makes sort of the climate system irreversible.
Okay,
but
sir.
I agree that losses are losses,
No, losses are losses, but you're talking turbulent dissipation is a different subject to me. Now, I've also taken the view with respect to everybody. Okay, one thing we do in statistical mechanics or statistical physics is we consider all collisions between molecules to be elastic. Now, they are inelastic. What happens is when two molecules collide, you get a deformation of the electronic cloud around there, and then you get a photon release. So what happens is the collisions are inelastic, okay? And so when you have turbulence, like you're talking from, I can't help but think that turbulence, if you have a laminar flow, the number of collisions between molecules is limited. But if you have a turbulent system, then you've got all sorts of collisions of the molecules, and all of a sudden you've got a whole bunch of inelastic collisions. You're going to create photons due to the distortions of the clouds around the molecules and electrons. And those photons are going to be lost because they're not going to be absorbed unless you have a wall that absorbs it. So same thing with in any closed system. You have gas, right? What happens is we have not only the molecules hitting the walls, exchanging energy with the walls, you also have the photons exchange going into the walls and being radiated. Now it's generally black body radiation, but call it thermal radiation. It depends on what the material is that's absorbing and collecting it. So thermal radiation, radiation is both absorbed and emitted back into a system. We don't define that in statistical mechanics. We define everything in terms of the gases, molecules, kinetic energy. It's rotational, vibrational, translational energy. And that is wrong because you're emitting the photons that reside in there. If you're going to try and tell me that photons residing between gas molecules is not energy, I'll shake my head. But in statistical mechanics, we limit it to that. So statistical mechanics is a approximation for systems where most of the energy all the energy is contained within the molecules themselves, the vibrational, translational, rotational energy. But it ignores the radiative energy in there. Now that is okay if you want to know the total energy of a system, and it works out fine for lots of experiments. The problem is photons travel at the speed of light. So if you want to go into heat transfer experiments, you're ignoring the fact that even though the photons represent a minute amount of energy in that system, they are transferring energy at a very fast rate because they go at the speed of light. Now, I'm sorry, but if we go back to your turbulence, okay, basically you can think of it. So you're absolutely right that energy is lost due to turbulence, but it's because they're inelastic collisions. If the collisions were all elastic in your turbulence, you wouldn't get a loss of energy.
May I just ask, because there does seem to be a difference in the way you're foreseeing things, but Robert Kay has made an expression, that what he claimed that Claes was talking about, he said this is called entropy. What is your position, Ken?
Entropy
Do you think that Claes has inadvertently dismissed the concept of entropy?
Well, 1865, calling it entropy was the biggest mistake ever in the science because it's led us down a route that does not work, right?
So you agree on that?
I fully agree on it. I can show it. I can show it mathematically. I can show it a lot of different ways. That's why I'm saying these 20 pages you might want to read, and maybe we can get together and have a better conversation because we're limited here. But I completely agree that entropy was, by Clausius, the definition was the biggest mistake ever. You see, you got to realize that the mentality of these guys, they had the Joule's experiment, and they're saying, they go, well, every time a system expands, it loses energy, right? And they couldn't figure it out, so they made entropy, and they could mathematically make it work. It's a mathematical contrivance that does not belong in theory. Okay, we're back to the Joule's experiment. There's no work done because you're going from a vessel, a gas, into a vessel, but you're not lifting the atmosphere. You understand? And they couldn't get around that mentality, so they got that. All the equations, like you get into the Poisson's equations, all those equations that are derived from saying, TDS equals the energy in, they're just approximations, and it can be shown that they're not proper equations for theory. So you got to watch yourself. You can have a mathematics that gives you approximations for everything, but it's not. It's a horrible math for theory. Okay, and that's what's happened with.
Okay, well, we have some agreement there, but with regard to the more detailed information, the 20-page document or whatever, Claes, have you looked at that, or have you any overview?
Yes, very briefly. But I think that we agree on several things. So what maybe we are not agreeing on is sort of the necessity of the appearance of turbulent dissipation in systems. And
no, I agree that I agree with what you're saying. I just don't think that you're thinking of it in the same terms of of energy being created due to molecules colliding, right? It's like the Stokes-Navier equation. I wrote a paper, I don't know, 2018, 2019 on it, but it never got anywhere, but that's okay. But I mean, the reason Stokes-Navier work, it's designed for like linear flows or with little changes, right? When you get a turbulent system, you've got a discontinuity, right? It's not a small linear change like a differential is made to be. It's just this huge abrupt change. It goes from here, then all of a sudden it goes up there, the change. So that the differential math becomes irrelevant. You know what I mean? Because differential math is about slow, continuous change.
Agreed upon is possibly the most controversial point. I mean, Robert Kay has expressed it. He said, entry is a measure, merely a measure of the losses in turbulence. But you gentlemen are agreed on that point, and yet you have other disagreements with.
But we have different ways of looking at it, and for our own reasons.
Maybe that's
I respect that. This is what life is about. But I mean, just adhering to the indoctrination given by statistical thermodynamics and by the idea of TdS equals dq is ridiculous, right?
Yes.
And we agree there.
Yes,
you're agreed on that.
But how we got there and our reasoning is different. But I think you should be able to respect the fact of what I'm saying. So the number one thing is to think about is I'll back down if you show me somewhere in thermodynamics where they show that the lifting of the atmosphere by an expanding system is work onto the atmosphere. You know what I mean? They don't. We don't respect that. And I mean, we've got other problems that are going to arise here, like the latent heat of vaporization. Latent heat of vaporization is the energy to break the bonds plus lift the atmosphere. Therefore, there's no atmosphere being lifted in condensation. So the energy in latent heat of condensation does not have the work term on it. It's just the bonds going back together again. I just shake my head. We can't prove that because we can measure the latent heat of vaporization in a calorimeter, but you can't do the same thing with latent heat of condensation. We just assume that it equals the negative of the latent heat of vaporization, right? But if you think about it, vaporization and condensation, two different processes, and one has work and one doesn't.
So in all these equations, change of state or whatever, you would see gravitational terms, would you, Kent, appearing?
I did. When I wrote the little note to Claes there, I started off by talking about, what it takes to lift the Earth's atmosphere, and that was in terms of gravity, the mass of the Earth and how much it's lifted, right? And that actually turns out to be equal to PdV of the atmosphere. It's the pressure and the volume change of the atmosphere. The problem is the system whose volume is changed. The system's volume changes. That system who's expanded is a subsystem of the atmosphere. Therefore, its volume change is the same as the atmosphere's volume change. So mathematically, you come up with the same thing. Okay. The pressure in front is the pressure of the atmosphere. So it's P, pressure of the atmosphere times dV atmosphere. That is the potential increase of the atmosphere, and it equals mgdh. Okay. And what happens is we do processes and we say, it's an isothermal isobaric process. Well, if it's an isobaric process, all of a sudden you can replace the pressure of the atmosphere, pressure atmosphere times dV atmosphere, with the pressure of the system, because the two are equal. It's an isobaric process. You understand? So we got these limitations that we don't really think of. We think of incremental processes. It's led us down a path that is illogical.
Okay, so basically, before we move on, maybe some other points.
I have to leave.
Claes, could you give just a brief response to Ken's position, and then perhaps we could move on?
No, I think we agree on basics. So that's fine. We agree that entropy you should not use this concept because it has no physical meaning that is possible to understand. and so we have losses that are necessary and gives a direction, and also concerning the action of the atmosphere, including effects of gravity. I think we agree on a lot, so that's fine. Yeah.
Can I email you the papers that I wrote yesterday?
Yes, of course. Yes, do that.
Anybody else want them, or can I post them anywhere?
Yes. Well, we can communicate by email.
I sent you an email. Communicate.
A URL.
Yes.
Nick early on said that if you were not here, we could show this video, which I don't think we have time for. But anyway, we'll see how it goes. Which he's claiming that would answer the questions that I think appeared in Claes's summary sheet. It's this video, 29 minutes long. He gave us a URL to that.
Okay.
You know what we're talking about, yeah. Well, I mean, if things peter out, we can show that video.
But I have to leave now. Hello.
Hello.
So, yeah, you're there, Chris. So I'm just we're doing very, very well with regard to the discussion because you finished nice and early. But you said you'd probably have to leave after an hour. Is that very serious?
Yes, I have to leave now. Yes, yeah.
Okay, so I just want to give, if that's all right, Kent, if I may just bring you down for the moment because we'll come back.
Yeah, no, that's fine. I could go on for 3 hours, 5 hours.
Yeah,
so
okay. Well, we have another hour.
And I gotta understand.
After Claes is gone. So what we'll do is, if there's any quick question that anybody wants to put to Claes from the green room, James Aratun does. So James, I'm bringing you up, and Claes is disappearing. So if you could be brief, but please give your point. No, can't hear you. You're mute. You have to unmute yourself, James.
Okay. As you can hear me now.
Yeah.
Right.
Yes.
There's two quick things. In the chemical, in the paints industry, for example, 2 different paints, you mix them in. You don't have. It's not together. Not based on the process, but the mixing. There will be heat involved, and that sort of mixing of 2 different substances is not really in your theory. Could you make a little comment on how that comes about? That is a sort of classical entropy type.
Do you want to unmix them or what? Or
you can't unmix them. It's a sort of entropy.
Is this what you want? Okay.
Yes, but
do you want to understand why you
it's a one-way process?
So you want to understand why you cannot unmix?
In your theory, or is
irreversible?
Not really part of your?
Well, because it is when you mix them, you create lots of microstructure. Which, in order to unmix this microstructure, requires infinite amount of work or something to unmix, because it is fine structure, and each little piece of that has to go one way and the other way. So it is by finite time, precision, computation. You cannot do it. You could try to unmix, but you will not succeed. You could try a little bit. You could try, but it is impossible because there is a limitation of the precision that is available.
So many
do you have an alternative explanation, James? You use a concept.
I don't. But many people say it's the statistical, with calculation, which Claes is saying is wrong.
No, but it's easy. You crash, your cup, and then it's impossible to get it back in shape because there are so many little details. So it will take infinite time of work, and you cannot do it. So it is not more that's quite obvious,
I'll have to think about that.
Okay.
Let's do one quick comment. There's 3 theories involved in thermodynamics. There's the mechanics, electromagnetics, and there's the quantum theory. 2 of them are reversible. Electromagnetics, if you light a lamp and light spreads out from the lamp, it's irreversible because you can't get the light back into the point. It spreads out from the point. And so I always ask the question, everyone goes quiet when I ask it. electromagnetics is fundamentally irreversible, isn't? And this is part of the argument Kent was saying. It's basically down to how light is spreading out that's causing the irreversibility.
Well, maybe in that sense, everything in the universe is irreversible because you could never get it back precisely to an earlier.
Yeah, big things.
State.
Macroscopically you can move your furniture around and you can reverse it. So it is macroscopically it's possible, but not microscopically. That's the basic thing. So
I'm just saying from point of view of fundamental theories involved in thermodynamics, and there's only mechanics.
Right, but the enigma is if the system is formally reversible, like quantum mechanics, why isn't it in reality irreversible? Why is it in reality irreversible? This is the big thing. It looks reversible.
It's probably not the whole story.
And Newtonian mechanics looks reversible, but it is not. The question is, why is it not realistically reversible when it is formally reversible? And my answer is finite computation. Okay.
Yeah, but the theory depends on it being irreversible because Lagrangian mechanics and Hamiltonian mechanics don't allow dissipation. That's part of the deal you take. We take in those.
Yeah, it is. Formally reversible with us. But if you look, the details. Okay, the details. Well, anyway, so I have to thank you. Sorry.
Okay, thank you very much. I'll bring you down, James. Okay, I'll let you say a few words yourself, Claes, just in summary before you go, uninterrupted by my voice or anybody else's. So the floor is yours for a minute.
I can just say that if you have some interest in what I have said, there is a lot on my web, my main blog, where you can find lots of material. So on many aspects. So I hope you go there and look at my blog, and hopefully you will find something that can amuse you a little bit. So that's what I hope you can do. Thank you.
Well, I'd like to thank you very much, Claes, today for coming today. I mean, I know you have another pressing engagement, which you're going to now, but thank you very much for giving us this hour of your time. And I can certainly say I've had a quick look at the blog, and there's so much information there. You could actually very usefully spend a lot of time studying the material, theoretical and practical and philosophical and even literary and so on. So I think you've given us a very good introduction. It's very, very brief. It's got us talking, and we'll actually continue talking when you've gone. And if there are any questions, as I said earlier, that cannot be answered, we will forward them to you. So I'd like to thank you most sincerely for agreeing to talk to us again.
Thank you.
And I know we're talking about maybe a more full presentation at some stage in the future.
Yeah, there is
thank you very much for making these last minute arrangements to come here today. It has saved our day, and it's given us a lot. So thank you very much.
Thank
and we hope to see you again. Thank you.
Bye.
Goodbye. Goodbye. So, everybody, we have choice. A lot of discussion has been started from Claes's presentation. Now, we can continue. We must continue. But would anybody like to spend the next 29 minutes looking at Kent's video, which was referred to? I'll only do it if a majority of people want to do it. So, does anybody in the green room, if anybody in the green room would like me to put up this video, just raise his hand. So let's see. We have one, Danny, and Slobodan two. And actually, John wants to see it. Nick is being shy because he suggested it, but he's put up his hands. There's four. And Kent won't say anything. He's very shy. Okay, well, I think we have a majority for having a look at the video. So why don't we just spend the next 29 minutes looking at that, and then we can have a wrap-up discussion. And I hope the people on the Facebook and YouTube find it interesting. So I'll have to share my screen again. Just give me a moment to do that. Share screen. Entire screen. This. Let's see. Can I get the audio? Also share audio. Share. Let's see. Can we get it up now? It's taking me another. That's strange. Well, the best laid schemes o' mice and men gang after Claes, as Robbie Burns said. It just gave an error when I put in the URL which Nick posted earlier on. So I don't know what the explanation for that is. Is that working? That URL? Let me see now. I get rid of all that. Okay. So I'll click on it once more to see does it work. No, there's a problem with it, I think. No, oops, wrong. Okay. So I think we'll have to give that a miss. I will pop the URL into the chat in case any of you. I thought I could do that. It's not working. Let me see. Yeah, I'll bring you in now in a second, Nick. I'm just popping that into the chat, just so everybody has it, and I'll bring you in. I hope you can help me because I'm in a bit of a bind at the moment. Okay, I've done that. Now, okay, and I've done that. Now you're back, Nick. Can you?
All right, try the one I just put in above the one that you put in. Apparently, I was in studio or something like that.
Oh.
So that goes directly to it.
Okay, I'll try that, and if it works, I'll then share my screen. Yeah, that seems to be working. Okay, thank you. So let me stop it. Let me that. Let's see now where we are. Okay, let me go back to StreamYard, and I'll share my screen and put in that new link you've given me, Nick, and I'll bring it down now. Okay, now let me see this work.
Well, the first thing we need to do is...
Okay. Hello, everybody. I'm Kent Mayu, and we're going to talk about new thermodynamics, and we're going to challenge entropy in the second law. Fundamentally, there are issues with the second law, and one the other is human stupidity. I don't so much think of this as human stupidity, but mainly it shows that you can program a human to believe almost anything. Even people who are smart for humans can be programmed. Okay. So let's take a look. The basics of thermodynamics is how work and energy interact with matter. An isometric box or a system into which energy enters, dq in. And that system does work onto something. Okay, a machine could be anything. One could write the following first law style equation differential form. dq in equals dE system, change energy of system, plus the work out, dW out. Now, one is a very generic equation, and it assumes 100% efficiency, only one and the same. Now, we consider work is done by raising a mass by a height dH against Earth's gravity. Now, equation one becomes a little more clear, and we go dq in equals dE system plus mg dH. Okay, and mg dH is the work to raise a mass. Okay, now this is equation two. It still assumes 100% efficiency. Okay, as the mass be harnessed by tying a rope onto the mass and letting the mass fall, in which case the rope can pull on another object and do work under the other object. Or one could simply let the mass fall, in which case its potential energy is converted into kinetic energy. Right? But instead of being nondescript, as equation 1 and 2 were, consider that the system doing work is an expanding system on Earth's surface. Okay? So the expanding system is surrounded by Earth's atmosphere, hence one would write dq in equals dE system plus the work term, and the work term is PdV atmosphere required to lift the weighting mass in a gravitational field. So any system that expands has to lift that weight. It doesn't matter what direction it expands, but it has to lift the weight upwards. Okay, if one removes the mass from on top of the expanding system, then m equals 0, and equation 3 simplifies into equation 4. So work to lift the atmosphere, PdV atmosphere. In terms of the expanding system, the work done under the surrounding atmosphere is lost work. So we can write dW lost equals PdV atmosphere. Hence, you can write equation 5, which is thermodynamics. Lost work, once more, equation 6 is emphasizing what lost work is. It's work done onto the atmosphere. Why is it lost work? Well, you can't recoup the energy. You cannot tie a rope onto the overlying atmospheric gas molecules. Hence, the work is lost. And any expanding system on Earth's surface becomes an irreversible process. Okay, or the expansion of any system on Earth's surface is an irreversible process. If that expanding system contracts, then the energy used to raise the overlying atmospheric gas molecules remains lost, at least in terms of the expanding system, right? The work isn't lost because the expanding system lifted the weight of the atmosphere, increased the atmosphere's potential energy, if you prefer. So in reality, the expanded system contracts, the overlying molecules now come crashing downwards, increasing their kinetic energy. This can be viewed as heat. I mean, kinetic energy of a gas molecule is considered heat in many ways, right? So you can consider this as heating of the atmosphere. It's really not increases potential. If I let that rock fall or lift that mass fall, its potential energy is transformed into kinetic energy. But it's mean that I don't gain it back, right? It just bounces off my noggin. Right. So let's talk about how entropy became a blunderous, it's hard for some people, but let's just call it blunderous entropy right now. System, right? We have dq in equals dE system plus PdV atmosphere, that being the work in the atmosphere. Now, Claes coined the term entropy in the mid-19th century as something that when multiplied by temperature defines energy, right? Yeah, that came from a Greek term, but it doesn't really matter. One may now choose to rewrite equation 4 in thermal entropy change. You put TdS equals dE system plus PdV, right? Problem is, equation 7 lacks lucidity of having the subscripts that clarify that PDV is work done under the surrounding atmosphere. Now, this is important, okay? One might naively envision equation 7 as follows. TDS system equals DE system plus PDV system. In other words, equation 8 is thinking of everything in terms of the system, right?
With the world in chaos, what's really needed is someone to finally make sense of human seemingly mad behavior.
The work done is done onto the the work done is not done onto the expanding system. Rather, it is done by the expanding system onto the surrounding atmosphere, as was described before. Remember, we've lifted the weight of the atmosphere upwards, right? So writing it equation 8 in terms of the system is sort of a little iffy. I mean, you can think of it this way. I mean, the energy of the system changes DE system. Well, that includes all the microscopic energies inside the system. So PDV can't be part of the system. Okay, if all the energy in the systems changes, so then what's PDV? So let's continue with the traditional indoctrination and rewrite equation 8 without the clarity of any subscripts. You get TDS equals DE plus PDV. We find this in all sorts of textbooks, right? One can use differentials, you know, and we learned this in first and second year calculus, and claim that TDS equals DST minus SDT, and we do the same thing for PDV. There's nothing wrong with that, except that we're talking, well, we're going to see what's wrong here. So we got 9 and 10 and equation 11. Now, substituting 10 and 11 into 9, you get equation 12. Okay, and equation 12 is the first step in obtaining the so-called free energy, such as Gibbs free energy and Helmholtz free energy. It's used all the time in chemistry and in physics and stuff like that. The issue arises, so if PDV concerns the atmosphere, while TDS is energy into the system and DE is the expanding system's energy change, then does it make sense to substitute 10 and 11 into 9? I mean, it makes sense if you just look at it as written, but when you clarify what each parameter is and it's describing, it doesn't make sense, okay? If it makes sense to you, what does it all mean, right? I want to emphasize this. If you're not convinced about equation 12 being nonsensical or nonsense, then think of it this way. The surrounding atmosphere remains isobaric, right? It's massive. You can do little things. You can change the pressure in little locales and stuff, but eventually it's going to go back to this isobaric state, right? Thus, VDP at zero, which is VDP in equation 12. The implication becomes that equation 12 is nonsense. Now, I've talked about this in more detail. You might want to read my paper, you know, New Thermodynamics Reversibility 2020. But I basically I give another explanation for Gibbs and Helmholtz free energy on that paper. I mean, we can give another talk about it, but right now we're just talking generalities in thermodynamics, okay? So why use entropy? Well, entropy, or Clausius entropy, is a mathematical contrivance. I first talked about this in 2015 in a paper in Physics Essays, but this sort of expands it a bit. The contrivance allows for all those logarithmic functions that are vital to thermodynamics. Right? We have logarithmic functions everywhere in thermodynamics, and it's necessary because things happen exponentially. That's fine. But the danger of logarithmic functions is that more than one function can be normalized to match one's experimental findings. And so there's no uniqueness to an equation and an experimental findings. There's usually a series of equations that can be normalized to your experimental findings. So it's a very dangerous when we talk about probabilities of heat exchange and stuff like that, but that's for another day, okay? Fortunately, thermodynamics logarithmic functionality can be explained in other simpler terms. Okay, consider how much work is required to compress a gas. For infinitesimal compression, in terms of the gas inside the piston cylinder, the isothermal work required for compression, WA to B, is an integral of increasing pressure change over decreasing incremental constant volumes. So one may choose to write it in terms of the gas inside a piston cylinder that's being compressed, right? And you can write it in terms like such as equation 14. As the gas's pressure increases, an increasing amount of infinitesimal work is required to compress the gas another incremental volume, right? And you can imagine that. So this is an example concerning why, in terms of the gas inside the piston cylinder, the work can be expressed in some natural logarithmic form. Now we should emphasize that equation 14 is for an isothermal process. So if I compress a gas, right? But if you do it quasi-statically, which means very slowly, then you can allow time for the heat to escape out through the walls and into the surrounding atmosphere as you compress it. So it can be an isothermal process, constant temperature process. If the piston cylinder is fully insulated, it's not an isothermal process. But again, that I'll talk about that another day if given the opportunity, okay? So instead, the point I want to drive home is now consider a gas inside a closed system expands. In terms of the gas inside the piston cylinder, the isothermal work is WB to 2A. It is again an integral, and this time one contemplates it in terms of incremental pressures multiplied by infinitesimal volume increases, right? So we get equation 15, or equation 15 is an example of that form, right? Once again, equation 15 considers isothermal, so it's for quasi-static processes where heat can go out, heat can be exchanged from the surroundings into the expanding system, okay? And it is pressure increases, the amount of work that an infinitesimal volume of gas can do decreases, okay?
Experience Cliffs of Moher with Ireland's leading tour operator.
But one can realize that an expanding system, I mean, if you think about a system expands isothermally, right? That means that its temperature remains the same. And just because its volume goes up and its pressure goes down, its energy doesn't change because it's isothermal, right? So you can quickly see through equation 15 by realizing that the work done by the expanding system is onto the surrounding atmosphere, PdV atmosphere. One often chooses to express the work done by gas in terms of the expanding gas. This is done traditionally too often without any necessary clarification of what you're describing, right? I mean, if you can imagine, if the gas expands, it expands isothermally, its energy really hasn't changed, okay? But it's done work, okay, onto the surrounding atmosphere. Thus, one can see where the confusion lies, or lay. Again, the work is always done under the surrounding atmosphere. So I repeat, work done equals work atmosphere equals PdV atmosphere. The rate at which the expanding system can do work under the surrounding atmosphere decreases as the expanding gas's pressure approaches that of the surrounding atmosphere. Equation is a rate-based equation. If you think about it, it should be rate-based and not written as 15. Importantly, if one continuously heats the expanding gas, then the gas theoretically can continuously expand both isothermally and isobarically, right? So a more pragmatic understanding may be deduced by considering two systems of thermal contact, thermal and physical contact, such as system A at a higher temperature and pressure than system B, right? So the hotter system A can pass thermal energy onto system B, and higher pressure system A can do work onto system B. Right? There's nothing magical about this. Importantly, the rate of heat transfer will decrease as the temperature of A approaches B. Hence, in terms of some constant, you can write equation 6. In terms of some constant A, you can write equation 17, which is very similar to 16. If B was our atmosphere, then the pressure of the atmosphere would be considered as constant. Okay. So the above formulas lead to two important considerations. Choosing to use entropy-based second law to explain why a system's energy degradation is a overcomplication. Certainly, a system's capability to transfer thermal energy or to do work can be explained in simpler terms. And really, the logarithmic functionality we saw are rate equations, as shown by 16 and 17 on the top, right? So those logarithmic functionality or natural logarithmic functionality that's so often associated with entropy in thermodynamics can now be explained with superior clarity if one actually expunges the notion of entropy. That's tough. Okay. Now, expunging entropy took me a long time. I mean, I rewrote, I was the first one to actually properly describe how much energy it takes to form a bubble, and people shot a laser into degasified water, and they figured out the energy to form the bubble. And it was sort of one of the reasons why my first paper was published in Physics Essays in 2004. But I realized at that point that there's something wrong with thermodynamics. And it took me a number of years to realize entropy was a problem. As soon as I threw entropy out of thermodynamics, it became easy to write. A lot easier to write. I shouldn't say easy, just became a lot easier. Okay, but the implications of entropy and lost work are profound. So let's look at enthalpy here for a sec. Enthalpy change is equal to dE, which is actually a change in energy in the system, plus PdV, and that is the work done onto the atmosphere. Now, equation 18, I'm sorry I didn't write it with clarity, but it joins around because the way it's written, someone might actually think it's all about the system. You know, it's not, okay? We're all about the isobaric expanding system in the case of 18, okay? Consider the enthalpy of vaporization versus enthalpy of condensation. Enthalpy is nonsensical. Then we should go back to maybe the term latent heat. And we used to use latent heat 50 years ago as a term, or 40 years ago, right? But we've now used enthalpy is more acceptable. Well, now I'm challenging that, okay? Since lost work is done onto the surrounding atmosphere, it only applies to expansion. In which case you might think of it as this. The latent heat of condensation is no longer equal in magnitude and opposite in sign to the latent heat of vaporization. This will strike people as odd, okay? But let's consider this. So the latent heat of vaporization is still, du plus PdV, the work done under the atmosphere. Now, I'm using a different nomenclature than is normally used. I've used it in a few papers, but the reason why is that L to G signifies liquid to gas, and then indicates the change from the liquid to the gaseous state. L represents, like I said on the previous slide, I don't want to use enthalpy anymore. It's too misleading, okay? But the latent heat of vaporization is again shown up top of equation 19. But lost work is irreversible, even for boiling water. Okay, so when you boil water, you don't get PdV back, right? So the latent heat of condensation does not involve lost work. Therefore, it's really just about the changes in the bonding energy, right? And I write latent heat of vaporization, gas going to a liquid, okay? The magnitude for the latent heat of vaporization is greater than the magnitude for the latent heat of condensation. You can see that if you compare equation 19 and 20, right? So why the mistake concerning latent heats? Well, there's a few reasons for it, but unlike the latent heat of vaporization being readily measured in an isobaric calorimeter, the latent heat of condensation cannot be so easily measured. Now, I did read a paper in the 19th century by Johnson, but sorry, I should know it. But anyways, it was sent to me by an acquaintance and stuff. And he talked about measuring the latent heat of condensation, but never became something done in practice. And the reason is it's just not as easy to measure as latent heat of vaporization. I'm not even too sure how you do it, okay? But we also have to add on to this the illusion of reversibilities. And this is really Locksmith's paradox. I mean, he wrote this in about 1870, or the paradox, somewhere around there. And it helps, Locksmith's paradox is basically you boil water, you heat something up, it expands, and then you stop heating it, and eventually it will compress back to its original state, right? But the point is, it took more money or more energy to expand the system than you get back. But you have the illusion of reversibility because because the system that you're heated is back at its original state. So this is really what Locksmith's paradox is. Okay, it's paradoxical. It takes more energy for it to expand. The forces of the atmosphere pushing everything back, and all the heat was allowed to escape out of the system anyway. So you went back in as easily as it takes the heat to go. You can understand where the problem is. It's sort of, you know, it's sort of you're damned if you do and you're damned if you don't, right? So anyways, it takes us to the second law. Sir Arthur Eddington is quoted as saying that the law that entropy increases, the second law of thermodynamics, hold, I think, the supreme position among the laws of nature. Now, Eddington was a big star guy in the 1930s and stuff like that, very well-known physicist. But the point is, he also talks about anyone that challenges the second law is really in for life of humility. I'm sorry, I don't know the words exactly. You can look it up. But anyways, so challenging the second law is sort of, anyways, you're going to be humiliated if you do it. But I can't stop but challenge it. You can see where the problems are. If one abandons entropy and it's accomplish the second law, then one's challenge Eddington's words. Explain why systems are inefficient or why one cannot have perpetual motion. It is often used in terms of increasing entropy. Entropy always increasing, and that's problematic as far as I'm concerned, okay? So we're going to continue this. So this is from my fourth year text, Statistical and Thermal Physics. It was done by Frank Reef, and it used to be my Bible, but now I realize where the problems are. And he talks about an equilibrium macro state of a system can be characterized by the quantity entropy, which has the following properties, okay? And basically 21 is the relation. Okay, so entropy times temperature is dQ, and so you get 21. But the main thing here is I want to go down to the changes from simple enough, right? But I repeat that statement on the very top, right? And the thing is isolated system. The problem is that an expanding system on Earth's surface is not an isolated system. It's expanding, so it's lifting up our atmosphere's mass, its surroundings, right? It's not isolated, right? You can imagine before when you didn't have clarity on PDV, this sort of would go over your head real easily. But things are not isolated. If it's not isolated, second law is not a rational law, and it isn't. Okay, at least in terms of entropy. When they talk first in vision, it was more or less about you can't have perpetual motion, all that stuff. But when you start explaining it in terms of entropy, it loses its rationale. So the second law of perpetual motion. I mean, perpetual motion implies movement. Anything in Earth, anything in motion on Earth experiences friction with the surrounding atmospheric gas molecules. We call this drag, okay? This is why a clock's pendulum requires a spring. It's also why your car requires energy to keep moving after you've stopped accelerating. You've hit your highway speed of 60 miles an hour or whatever it is, so you're no longer accelerating. But drag means that you still have to put your foot to the pedal, okay? So never forget that internal moving parts also experience friction in there. That creates heat. Importantly, expanding systems that often power devices must witness lost work as the surrounding atmosphere's potential energy increases, in other words, as the surrounding atmosphere is lifted. So you can start seeing the second law is an overcomplication of reality. You don't have to explain this in entropy. You got very fundamental explanations, right? So, but there's more to inefficiency than this, okay? We use gases all the time for bases. I mean, that's the basis of the steam engine, right? Water changing into gas. The energy of a gas is often written 3 PV/2. is PV. And you can see that all of a sudden there's a fundamental difference between the energy of a gas and its ability to do work. And the amount of work that an expanding gas does onto the surrounding atmosphere is lost work, PdV atmosphere. Okay. Now, the reason that 23 and 24 exist, it's really got to do with how much flux a container of gas can have. Okay. So the flux onto a wall to push the expansion, so only 2/3 of the gas's total energy can be used. Now, the math behind the flux is fairly complicated. It's in the book by Frank Reef there that I quoted earlier. Okay, and I've written about it a few times, but it's really pushes me to the limit. I'm sorry, I've been a long time away from this sort of math and stuff. But anyways, you can understand that only 66.67% of a gas's energy can be used to work. And this has to be ingrained into your head. So if not all of a gas's energy can be used to do work, you have inefficiencies, right? So the steam engine becomes so darn inefficient, right? It's something like 10%. I hear sometimes as low as 6 and sometimes as high as 12. But the inefficiency of the gas to do work, 66.67%. You have lost work, PdV atmosphere. You have dumping of the fluids. I mean, if I heat up a fluid and at the end of the cycle I dump it in the atmosphere, you've lost any energy in that fluid, right? So there's a few things that explain why, things are not efficient. And the likes of Carnot and Claes did not realize such things, okay? And the science has not progressed particularly well since the 19th century. I would argue that the science, because we made the mistake with Claes and his definition of entropy, has taken some obscure angles, okay? And everyone sort of believed it, and it just gotten into an overcomplication of the simple. A question for those who are not convinced about lost work. Traditional indoctrination fails to clarify what exactly lost. The notion of it can be found in various texts, is not all texts, and it's certainly not very clear. Right? I've given very, very clear explanation of why lost work exists. Right? Another way of viewing this, if you do not accept it, unfortunately, this means that thermodynamics, as is used in all the sciences, physics, chemistry, biology, cosmology, atmospheric physics, what have you, must be rewritten. This may be too much for those walking around in white lab coats. I mean, Tolstoy is one of my favorite quotes, even more so than the Einstein quote that I started off with. I know that most men, including those at ease with problems of the greatest complexity, can seldom accept even the simplest and most obvious truth, if it be such as would oblige them to admit the falsity of conclusions which they have delighted in explaining to colleagues and in the fabric of their lives. This quote about human nature, it applies to almost everybody, politicians, scientists, it doesn't matter, right? Nobody likes to admit that they made a mistake. And this is going to be tough. But unless you can explain to me, where the work, it has mass, it takes energy to lift any mass against the Earth's gravitational field. And this is what really got me started on the path I am on at this point. Thank you all for your time. Okay, I hope that you can think about this, even if you don't fully embrace what I have to say. I'd appreciate some thought and just some realization of what all this means. In part B, we'll talk about how this applies to statistical physics and where the errors are in there and stuff like that. It's all going to be a simple talk like this. Thank you again.
Okay, I think we're back now. Well, we've had the benefit of maybe two presentations, actually, because Claes's one was quite short, although we had a reasonably detailed discussion on it. And now we've had the benefit of Ken's presentation. Actually, we have heard from him before, so I think maybe for many of us it's not a total surprise. But I think that video was a nice summary of some of his ideas. And let's see if any of the comments come in from the social media first. That you've wasted our time, or we're delighted to hear that. They're thanking Claes actually. Okay, anything? Okay. Yeah, it's frictional heat. Rubbing atoms together is the excitement that causes heat. Let's see if there are any specific questions. Okay. Right. Let's hear first of all any private chat on it. James Keane is asking about some websites. I'm not sure if he's asking for Ken's or Claes's. Perhaps I could just written you up, Jim. Mind you, you might want to give us a bit of feedback on the two things, but you put a presentation. You couldn't find the URL on Google. I don't know which URL you're talking about. Is it Claes's or Ken's?
Well, actually, I was
but anyway,
looking for John Hodge's
any feedback, Jim?
But I do have a question
okay.
about the thermodynamics, if I may. That question is
yes,
this phrase finite precision. Does that imply that there's a minimum energy unit or value that applies here? Or what? I'm seeking clarification on the meaning of the term finite precision.
But is that insofar as it was used by Claes?
Yes,
or more generally,
it's used by Claes.
Because if you're a performer, I'm not sure we can answer it.
Well, okay.
So
I understand that, but I thought maybe some of the other people here might understand what Claes was referring to by the choice of the term finite precision. If there's nobody, I guess I can't get any insight into that right now. Okay.
Because one might say, if there's a division between finite and not infinite or not finite precision, where is that dividing line? It might be arbitrary. Okay. Well,
right.
Thanks very much.
In my work, I define a minimum energy value as a quantized minimum value. And so I was just wondering if Claes was perhaps referring to such a thing. But maybe James, other people have questions if there's no answers.
James Harrison has put a comment in that he thinks it may be a limitation of computer calculations. I'm not sure if that was what Claes was referring to, but it's one possible explanation of it.
Right. Okay. Thank you very much. Thank you, James.
Okay. Well, thank you, Jim. Okay. Is there anybody in the green room? Vladimir actually has put up his hand. So, Vladimir, what are your comments? Positive, negative, on the fence? What's your feedback on the two?
Let me tell you, or let me remind you. Thank you so much for a very good presentation, interesting presentation. But always I am thinking about physics like an experimental science.
You've just frozen there. Let me see now. I don't know why he's frozen there. It's strange now. Sometimes it happens for a split second, but it's continuing now. So I don't know if I put you up again. I think the connection is gone. Okay. We're going to see. Maybe he can come back presently. Okay. Sorry about that. Okay, Danny actually has put a comment in that he wishes to comment. So we're delighted to be able to facilitate that. All I have to do is sorry, Danny, I may not have seen your hand because you're down on my screen. But thank you for putting the comment in. So go ahead.
Well,
what's your take on it?
In physics problems, when you're integrating numerically a differential equation, you have a certain number of digits to get for your answer at the end to be correct, even assuming if the physics formula is correct. To integrate the ordinary differential equation, you need a certain amount of precision in order that the answer will be accurate, even though the physics is accurate. So, and usually if you're first order integrating or second order ODE, if if you think of in terms of second order being an acceleration double time derivative of a distance, if that's very large, then you need, especially if it's rapidly changing, you need more and more precision for your answer to make sense, even though physics may be correct. Relies on having enough digits so that you can take into account rapid change. So now some things like the weather, they try to simulate the weather based on fluid dynamics and whatnot. But it requires too much precision to predict more than a few days in advance. You need your instruments for measuring pressure and so on have to be extremely accurate. And even then, you can't get more than a few days predictions being halfway right. So
right.
It's not a matter of physics so much as a matter of mathematics. The physics can be completely and totally correct, but if say the acceleration is rapidly varying, then you need more. The more rapid it varies, the more precision you need for your answer at the end to be correct, even though the physics may be correct.
Okay, so it is a computational problem after all. Well, thank you for those comments, Danny. Thank you very much.
You're welcome.
Now Vladimir, there was a comment that came in that you had disappeared into dark matter. You had disappeared into dark matter, but you're back now.
No dark matter. Sorry.
No, it's a joke. You went black,
and
you would become dark matter. It was a joke.
Important in cosmology, but we are talking about thermodynamics now.
Yeah,
and
right.
some definitions, because in his theory, I don't understand what does it mean: temperature, pressure, volume. He used all these definitions, all these parameters of the medium or something I don't know, and where they came from. Because from statistical physics, we know what does it mean temperature, what does it mean pressure, but in his theory, he canceled statistical physics and he didn't give me any information about his definitions: temperature, power, pressure, all this stuff, energy. He, like a theoretician, it's playing with some differential equations, and there is no answer about the definitions of these physical parameters. The second point is, what is the thermoequilibrium of system? What does it mean? And what is the most important? He introduced these turbulences. They have angular momentum. My question is where it came from. You know, so many questions. You have some very good answers, conclusions, but you didn't specify even the beginning of your theory. What does it mean? What is the temperature? I don't know. In Maxwell statistical analysis, we know this is an average kinetic energy of this system of some atoms, molecules, and so on and so on. What does it mean, black body radiation? I have no clue from him because he told something, a few words, but he didn't specify what does it mean, black body radiation. Because black body radiation must have some interaction with body. What kind of interaction? What does it mean? And you know, so many questions I asked.
So all these questions,
I would like to ask him.
Vladimir, just to clarify, they do relate to Claes's presentation, not Kent's video. Okay. Right. Well, there are more questions perhaps than answers. Thank you very much. We're going to have to note those, and perhaps you know, at a later stage, Claes might be available to give us a more detailed explanation, because there's a lot of information on his website and he only touched on some of these matters today. So thank you for raising all those questions, even though we've no answers.
Yes, you know, all this information which he had. First of all, start from the beginning.
Yeah.
Give me the definitions of all the values you are talking about.
If you maybe had time to go into his blog and had a look at some of those, and maybe come back to us at a later stage to inform us as to whether you feel he has addressed some of those points and just didn't make it clear today, or maybe he hasn't addressed them, that might be a useful exercise. So
okay,
thank
you
you very
so much
much
for your advice, but you know, even you were overloaded with his website. You know, I'm overloaded with my cosmology. I'm very sorry.
I know.
And I want to have a direct answer on my questions, not to read all these hundreds of papers based on a very good theory, but the beginning of the theory. That's it.
Maybe if it's clear that they still need answering, we're going to have. That's Robert K says, Vladimir, these are questions for Claes. That's quite true. So
maybe somebody can answer who saw this website of him, and he can answer the questions I ask right now.
Okay, thank you. Okay, well, time is the thief of. I'm thinking of Milton, aren't I? How soon hath time, the subtle thief of youth, stolen on his wing my 23 year? I think the thief of time, the thief of youth. Anyway, time has caught up with us again, and we must bring the proceedings to an end. I must say, I started today with some trepidation because it appeared that Claes had pulled out. He had a conflicting arrangement and he wouldn't be able to give us any talk. So I was looking at what we might use to fill in, and we have a few possibilities. But I had a couple of further emails with him, and I think maybe my gentle persuasion prompted him to make some changes to his arrangement to make him available for at least an hour. So he did. He gave us a very short talk, but we had a very, very long conversation. And thank you very much for all your comments. The people in the green room made some very significant comments on us today. And the fact that they weren't really answered just gives us further food for thought. But I'd like to thank also Kent for having come to us today, and Nick for having informed him and maybe being the conduit for that. But I'm delighted that we were able to look at the video, and sorry we're not able to engage in further discussion about that. We may indeed bring you back at a later stage, Kent, if you wanted to give us the material, maybe in smaller doses that we can digest. But you did say that you'd be very happy if we at least started to think about the points you'd raised. And for my part, I can certainly say that I'll do that. I'll give it some thought. I'm not convinced one way or the other, but I'll give it thought. And there are positive comments coming in about the chat and so on, and the presentation. for quite a few. Yeah, some people won't be able to come back to James Aratoon, but you're all happy that we had a sort of a conference today, which was sort of a mishmash of things, but I think it worked out very, very well. And I'd like to thank Kent again, and I'd like to thank, in his absence, because he's gone, Claes, for having gone to the considerable trouble of changing his arrangements, actually. And I think he had some maybe health issues early in the year. He couldn't give us a talk during the summer, so we postponed it, and then this came up. But anyway, at the end of the day, we had it. And I would just repeat what I said when Vladimir was speaking. Do have a look at his blog. It's most interesting. He's got so much information there, from the practical mechanisms of flight in heavier than air machines, to sailing, to statistics, which he decries except for financial or insurance purposes, and for fundamental problems in physics. So thank you all very, very much for your participation. Sorry if maybe there were some comments we haven't dealt with. Kent has just said, anywhere I can put my comments on Claes' paper. Well, there is, which I think Nick can give you all the information on this, Kent. There is a sort of, I don't know what it's called, a blog on the CNPS, which has been put up by, it's one of the subgroups put up by David Hilster, and you can actually post to that. So check that with Nick, and if you're in difficulties, just send us a note and we can clear that up. You could certainly put your notes on that, and it would be available. The other way of doing it, by the way, is to look at the recording and just put in some comments under that. You can do that. People don't use that very much. I saw a slightly frightening comment from Nick, actually. It's saying he saw it didn't seem to be recording. I hope that was only a little bug at the initial point. I dare say the recording is automatic and the recording should be available. So either put a comment on the recording or go into the CNPS blog. So I'm going to close the meeting now. Thank you all very, very much for your positive contributions and for participating. Good day.